So, we will look into static CMOS logic family. Why static? So, we will come to that later, but as I have said that CMOS is the de facto standard for this digital circuit digital gate realization now. We will see that in successive slides. Now, as far as this CMOS realization is concerned, so this is done on silicon. Silicon, as we know that it is a semiconductor, and pure silicon in a silicon crystal. So, it consists of these silicon atoms and they form bonds between them. So, there is no free carrier. So, neither electron not hole, nothing is free there. So, it is just forming a crystal like this. So, it does not conduct. However, if we add some dopant into it, so we can either add dopants like arsenic or this boron. Okay. So, this type of dopants group 5 elements or group 3 elements. So, silicon is a group 4 element in the periodic table. Now, if it has got 4 electrons at the outer valency. Now, if you are adding say this arsenic, then arsenic is a group 5 element. So, that is it has got an extra electron, and so that extra electron does not bond with anybody. So, that is why if you these extra electrons they can move freely. Okay. So, if you apply some potential, then these electrons can be made to flow very easily. So, by adding this extra electron in the or doping the pure silicon with arsenic, so we get something called N type semiconductor. In an N type semiconductor, we have got plenty of electrons available, which can be made to flow if we apply some potential difference. On the other hand, so instead of applying a group 5 dopant, so if we apply a group 3 dopant, so group 3 dopant they have got 3 electrons at the outer valency. So, there it has got a tendency to capture one more electron. So, in some sense it is like a hole that is there in the outer valency. So, that is why this type of dopants they are called donor, and they are called acceptor, and this has got a hole. Okay. So, group 3 they have got missing electron as if it has got a hole, and this type of semiconductors that you get. So, they are called they are p type dopant, and if you put this boron type of impurity into this silicon crystal, the silicon wafer, then you will get a p type semiconductor. Okay. So, this both N type and P type semiconductors are there in realizing different circuits, like starting your diode to transistors to MOS and all. So, we will be using them particularly in the context of this MOS transistors. So, a basic nMOS transistor, the operation is like this. So, we have got this bulk silicon. So, this is the bulk silicon. So, this bulk silicon, so you can say it is an wafer of silicon, and this is a p type silicon. So, this is doped with boron. So, that this is this rectangular region that we have drawn. So, you can take it as a p type semiconductor. Now, on that we have got two heavily doped region of p type of n type semiconductors. Okay. So, that is done by means of this diffusion process that you can learn in some course on VLSI design. So, this is some diffusion is done, so that you get this n plus regions, two such n plus regions. Between the two n plus regions, so we have got a silicon dioxide layer, which is an insulating material, and on top of the silicon dioxide layer, so we have got a diffusion of this polysilicon layer. So, we have got a deposition of polysilicon. So, what happens is that if you do not apply any extra potential, okay, so this p type voltage p type. So, this is the body or the bulk silicon. So, this is kept at a low voltage. Now, if this source body and drain body diodes are off, so how can this be off? So, if you do not apply any voltage to this source and drain, all these diodes are off. So, there will be no current flow. However, if you apply some positive voltage in the gate, so if I apply some positive voltage in the gate, then what will happen? Electrons that are there in this substrate, this p type substrate, so they will be drawn towards this region. They will be drawn towards this region. So, you have got the electrons coming here. So far I have applied only some gate voltage, I have not applied any voltage at source and drain. Now, if you apply some voltage difference between source and drain, okay, then these electrons may be made to flow from one side to the other. Like if we make this drain voltage high and this source voltage low, then the electrons will be drawn towards the drain. As a result, the current will flow from drain to source. So, when I do not apply any gate voltage, so this transistor is off, but as we are applying some voltage, gate voltage, the transistor is this on, and if we have a potential difference between drain and source, then the current will flow through the device. So, pictorially, so it is represented by a situation by a symbol like this. So, this is so this particular symbol, we have got two terminals, source and drain, and then the other terminal. So, this is called the gate or G. Okay. So, this is called the gate or G. So, when G equal to 0, then this source drain, there is no current flow between source and drain, otherwise there will be a current flow. So, these are the different combination, like say I can have as I was telling that this is the symbol, we have got three terminal, one drain terminal, one source terminal and one gate terminal. So, this gate is something like a switch. Okay. So, gate, when you apply a voltage here, when you apply a voltage here, then the gate, as if the electrons are drawn into this region, as a result the channel gets established or the channel, so this becomes on. Similarly, when is like if now if you have a potential difference between D and S, that is if G equal to 1, then there can be a current flow between D and S. So, this G acts as a switch between D and S. So, when G equal to 0, so in that case this switch is off, and when D equal to 1, then the switch, when G equal to 1, then the switch is on. So, when G equal to 0, the switch is off, when G equal to 1, the switch is on. That is for nMOS type of transistor. In PMOS type of transistor, what will happen is that, so this is the channel is made by holes. Okay. So, these are made by holes, and for making holes, so we have to apply a negative voltage. So, or you can say I have to apply a 0 here. So, if I apply a 0, then the PMOS transistor is on, and if I apply a 1, then the PMOS transistor is off. So, this way, this by controlling this gate voltage, so we can consider the transistor to be on or transistor to be off. For nMOS transistor, it is on if G equal to 0, and it is off, it is off if G equal to 0, and it is on if G equal to 1. For PMOS transistor, it is on if gate equal to 0, G equal to 0, and it is off if G equal to 1. So, in so we can use either of these two types of transistors, nMOS and PMOS transistors, and different logic families have been built, like say nMOS family that I have said. So, that actually uses this nMOS type transistors to get different types of gates like AND gate, OR gate, NAND gate, like that. PMOS also can be used for that, and in a CMOS, so we have got both nMOS and PMOS transistors for realizing the logic circuit, logic gates. Okay. So, a CMOS inverter looks like this. So, we have got this, this is the symbol of a CMOS inverter. So, upper transistor, so whenever we have got a bubble here, so this means this is a p type transistor. So, this is a p type transistor and this is an n type transistor. So, p type transistor means if G, if I say this is G, so this is a G1 and say this is a G2, when G1 is equal to 0, then P is on. When G1 equal to 1, P is off. Okay. Similarly, for n type transistor, if G2 equal to 0, then the n type transistor is off, then n is off, and if G is equal to if G2 equal to 1, then n is on. So, this is the situation. Now, let us consider the case where these two gate terminals of this p type transistor and n type transistor, they have shorted and the input A is applied to both of them. Now, what happens? Now, if A equal to 0, so if A equal to 0, in that case this transistor is as per this writing. So, as per this transistor is on and this transistor is off, fine. So, this upper transistor is on and lower transistor is off. Now, if I measure the voltage here, how much, what is the value I will get? So, I will get a value close to VDD, okay. That is VDD is say high. So, this is say some 5 volt, then I will get a 5 volt here. So, I can say if A is equal to 0, then I am getting Y as 1 logic high, which is say equal to 5 volt. Now, if A equal to 1, in that case what I will get? So, in that case this P is off. So, this is off now and this is on now, the lower transistor is on now. Now, if I measure the voltage here, I will get a value close to this ground potential, which is 0. So, I can say if it is 1, then I will get a 0 there. So, what is this functionality? This is nothing but an inverter. So, it is, so I can say this is an inverter. When A equal to 1, Y is equal to 0, when A equal to 0, Y equal to 1. So, this basic circuit, this basic circuit acts as an inverter and it has got two transistors of two different type, nMOS transistor and PMOS transistor. So, we call it the that is why it is called a CMOS inverter. So, it has got complementary metal oxide semiconductor inverter. So, complementary means it has got both P and N components in it and the input is feeding to both the N transistor as well as the P transistor. So, this way I can have this CMOS transistor, CMOS inverter. So, next we will be looking into a cross section, like how this CMOS transistor, CMOS inverter looks like. If I just take such a device which is nMOS inverter and take a cross section of it. So, normally what is done is that, so for as we have said seen in the first slide. So, we have got a p type substrate onto which we have got this we have got the n type regions. So, we have got p type substrate onto which we have got this n plus regions for the drain and source, and then in between we have got silicon, this is a silicon dioxide, okay, and here we have got the gate. Okay. So, this is the polysilicon gate that we have. So, these are the legends that we have used. Now, you see that these inputs are, so this is the, if this is the source, this is the drain. So, this is the source and this. So, for the p type transistor, what we have to do is I cannot use a p type substrate, I have to use an n type substrate. So, for that what is done, within this p type substrate one n type well is formed, okay, a region where I do some n diffusion. So, it creates an n type well, and within this n type well, so we do this p plus type of diffusion to create the p plus regions. Now, using this metal line, so this blue colored region, so this region you see that these two are shorted. Okay. That means the drain of the N transistor and the source of P transistor, so they are shorted. So, if I draw in terms of diagram, like if the lower transistor is the N type transistor, lower transistor is the N type transistor. So, this end is the source. So, this end, this point is that S that I have. So, this gate is there, then this drain is connected to the source of the P transistor. So, this is nothing but something like this. So, this is the P transistor. Okay. So, this is the drain and this is the source of this, this is the drain of P and this is the, so sorry. So, this is the source of P and this is the drain of N. So, they are shorted. Similarly, the drain of P, so it is connected to VDD. So, this is connected to VDD as it is shown here, and we have got these two terminals, these two gates are available. So, these two are to be shorted. Okay. So, these two are to be shorted and the A input has to be connected here, and I have to take output from this point. Okay. So, this is the shorting out of from the two shorting. So, this is the Y output which is going out. So, I can put some additional metal lines to kind of short the two gate inputs and apply A here. So, as it is shown here that the A is applied to both of them and Y is taken from here. So, this way we can have a N type we can have this CMOS inverter implemented using this CMOS technology. So, this A is going to both the gates and Y is taken from the shorted point of this source, this drain and source, drain of the P type transistor and the source of N type transistor. So, this way we can realize this CMOS inverter. Now, in general, so if you look into static CMOS family, then what happens is that so it can be, the whole circuit can be divided into two regions. One is called the pull up network, another is called the pull down network. So, PUN is the pull up network and PDN is the pull down network, and these inputs are connected to both pull up and pull down network. So, this in1, in2, in3. So, these are the three inputs, they are connected to pull up network and they are also connected to pull down network. And then output, so VDD is connected to the pull up network and this VSS or ground is connected to the pull down network, and the output is taken from the middle point of this pull out and pull down network at the from the shorted point of them, and you get the output as F. So, if we take the example of this NMOS inverter, CMOS inverter, you see the way we did it was like this, that this was a PMOS transistor and this was an NMOS transistor. So, this was grounded and the input A was connected to both, and we were taking the output from here. So, this was connected to VDD. So, this was the Y point. Now, you try to correlate. So, you see that input is, so this is my pull up network consisting of only one transistor and this is my pull down network consisting of again only one transistor. Now, you see the input is going to both pull up network and pull down network, VDD is connected to the pull up network and ground is connected to the pull down network, and the point of shorting between pull up and pull down network, from that middle I have taken out the output. Okay. Now, how does it operate? So, you see that whenever so in this in the case of inverter, what happens is when A was equal to 0, when A is equal to 0, then this transistor was on and this transistor was off. As a result, if you look into the current flow through the device, so there is no current flow from VDD to ground because this transistor is off. So, there is no current flow path from VDD to ground. Similarly, when A is equal to 1, then this transistor is off and this transistor is on. As a result, there is no current flow path from VDD to ground again. So, in case of static CMOS, whenever the input is stable, so whenever the input is 0 or input is 1, either the pull up network or the pull down network, so either of them will be off. As a result, there is no current flow path from this VDD to the ground, and that is why it consumes very little power. So, when this current flow path will exist? Only when this A makes a transition from 0 to 1. So, it is somewhat intermediary, say around 2.5 volt. So, around 2.5 volt, what will happen is that this transistor will be on and this will also be on. So, for that time there will be some current flow through this device, but that will last for a very small amount of time, because soon A will be going beyond 2.5 volt and as a result the upper transistor will be turned off. So, whenever this A makes a transition from 0 to 1 or 1 to 0, there will be some current flow through the device and it will consume some power, otherwise it will not consume any power. Okay. That is the advantage of CMOS, that it consumes very less power because there is no static current flow through the device. Now, this pull up network, it is implemented using PMOS transistors and pull down network is implemented using NMOS transistors. So, they are called dual network because here what the same functionality is implemented by pull up network and pull down network. Okay. One and another important thing that you get here, I am getting here y as a function where y is equal to a bar, y is equal to a bar. So, in general, so you will get the complement of a function like this. We will see some example that will clarify it. See, suppose I have to get this pull up network is the dual of pull down network. So, for example, if it is what is done is that in case of pull up network. So, if I am doing using say so, if I have connected say two transistors like this, two nMOS transistors A and B, okay. So, I am not drawing the pull up network, I am just assuming that there is some resistance here, and then from here I have taken it to some output y, and this is connected to VDD. Then what happens is that when this A and B both are equal to 1, then only you get a 0, fine. Either of them being equal to 0, output will be equal to 1. So, what is this logic? This is nothing but the NOR gate. Yeah, either of them being equal to 0, the output will be equal to 1. So, either of them being equal to 1, output is 0. So, you get a y equal to A nor B, any of them sorry, I am extremely sorry. So, this will be equal to output will be 0 when both of them are equal to both the A and B are equal to 1, and it will be equal to 1 whenever at least one of them equal to 0. So, y equal to okay. So, if any of them is equal to 1, then if both of them are equal to 1, then the output will be equal to 0. So, you get an AND operation NAND operation of A and B. So, any of the when both of them are equal to 1, then only output will be equal to 0. If any of them equal to 0, naturally there is no current flow path, there is no discharge path for this y to ground. So, in that case at this point if you measure, so you will get equal to VDD. So, you get a 1. So, this way I can see that if I put these two transistors in series, then I get the two nMOS transistors in series, I get the NAND function. Okay. So, for the PMOS part, what we will have to do is we have to take these two in parallel. Okay. So, let us see why. So, suppose this is my VDD, and here I have got this A and B, this is A, this is B, and I have connected these two, and there is a resistance here which is grounded, and here it is the output y. Now, what happens here is that, so here if I will get a 1, for getting a 1, so either of this A or B should be equal to 0. Okay. So, if any of them is equal to 0, then at this point if I measure a voltage, so I will get a equal to VDD. But if both of them are equal to 1, then there is no current flow path. So, as a result I will get a 0 there. So, this also realizes the function A equal to A B bar. So, the same NAND function when you are putting them in nMOS transistor, so you are getting them connected in series, and if you are putting in PMOS transistor, so you have to connect them in parallel. So, that is the duality between this pull up network and pull down network. Since these PMOS transistors are implementing the pull up network and these nMOS transistors are implementing the pull down network. So, whatever you connect in series in case of pull down or nMOS network, so you connect them in parallel in the PMOS network or pull up network, and vice versa. So, whatever is connected in parallel in the nMOS network or pull down network, so you connect them in series in the pull up network. So, that goes vice versa. And another point is that you will never get a true output in the y, like you cannot get say y equal to AB. So, this is not possible using this CMOS family. So, you cannot get y equal to AB. So, you will always get the NAND function. Okay. So, you will get the NOR function, or you can get the inverter function, but you cannot get AND OR things like that. So, that type of functions cannot be obtained. However, that does not matter much, because if you need an AND gate, so you can first realize one NAND gate and follow it by an inverter. So, that can be done. So, that way we can realize in CMOS family. So, we can have this NAND gate followed by inverter to get AND gate. So, how do we realize the NAND gate? So, here is an example. So, you see, suppose I have got, this is the NAND gate truth table 0 0 1 0 1 1 1 0 1 and 1 1 0. First, so this is the corresponding circuitry as I was telling. So, there will be a pull down network consisting of nMOS transistors, and there will be a pull up network consisting of the PMOS transistors. And if you look into these two networks, so they are dual of each other. Like whenever I have got these nMOS transistors in series, so corresponding PMOS transistors are in parallel, and we will see vice versa. So, if you put this nMOS transistors in parallel for some circuit requirement, so you have to put the nMOS transistors in series. So, let us see the combination that when this A equal to 0 and B equal to 0, output is equal to 1. How does it happen? So, both of them are equal to 0, means both the P transistors are on and both the N transistors are off. As a result, if you measure the voltage, so you will see the voltage value equal to VDD. Similarly, if it is 0 1, so A transistor, so this is 0 and this is 1. As a result, this transistor is on and this transistor is off. Similarly, this transistor is off and B transistor is on. However, since these two are in series, so it does not matter. So, there is no path from this output to the ground, but there is a path from VDD to out via this A transistor, because A is equal to 0. So, you get the output as 1. Similarly, when both the inputs are equal to 1, then both the upper P transistors are off and both the lower N transistors are on. As a result, there is a current flow path from this output to this thing. So, you get a voltage equal to 0 at this point. So, that way this particular circuit, it can realize the NAND operation. So, you can so in general we can say that this pull up network, pull down network is AB and pull up network is A bar B bar, which is AB bar. So, that is conduction to VDD and this is conduction to ground. So, we can also realize NOR gate in a similar fashion. Like for NOR gate, we have to do this A and B in the pull down network. This A and B, they should be connected in parallel, and in the pull up network, this A and B, they should be connected in series. So, whenever it is this lower network is in parallel, upper network is in series and vice versa. So, here we can quickly check that when A and B both are equal to 0, output is equal to 1. If A and B are both equal to 0, then both the lower transistors are off and both the upper transistors are on. As a result, at this point you get the voltage value equal to VDD, and if both of them are equal to 1, then both the transistors, lower transistors are on and both the PMOS transistors are off. As a result, at this point you will get a 0 volt. Okay. So, this way we can realize this NAND gate and NOR gate in CMOS family.